Hello students, welcome to the online video lecture on microprocessors and microcontrollers theory. Myself Dev Kumar Choudhury, and we are starting today the instruction set of 8085. First of all, I would like to ask you whether am I audible or not. Am I audible or not? Is my screen is visible or not? I'm waiting for your reply. Am I audible? If my screen is visible to all of you, I am not getting. I am waiting for your reply. I am waiting for your reply. Please reply, then we can start. Am I audible to all of you? If I am audible, then please write it down. Yes, sir, you are audible. Moinak Roy is writing, yes, sir, you are audible. Is my screen is visible? Is my screen is visible to all of you? Okay, thank you. Then I shall start. Hello students, welcome you all to the course Microprocessors and Microcontrollers Theory. Today we are discussing chapter number 1 of module 2, which is known as instruction set of Intel 8085. This is our lecture number 3. In earlier lecture we have discussed data transfer instruction, logical instruction. Today we shall concentrate on arithmetic instruction. So without wasting any more time, let us go to the arithmetic instruction. So in case of the arithmetic instruction, we are observing that an 8-bit number or the contents of register or the contents of memory location can be added to the contents of accumulator. So conclusion is all the arithmetic instructions are basically one address instruction. All the arithmetic instruction mostly require either 1 byte or 2 byte. If they are in register addressing mode or memory addressing mode, then they require 1 byte. If they are in immediate addressing mode, they require 2 bytes. So the content of the accumulator, for example, say add B instruction, what happened in that case, the content of accumulator is basically added with the content of B register and the result is stored in A register. Another example, say ADI 05H. So what happens in that case, the content of the accumulator is added with the 05H, that is the hexadecimal data, and the result is stored in the accumulator register. Another example, say add M. In that case what happens, the content of the accumulator register plus the content of the memory location is added, result is stored in accumulator register. That's why it is saying the content of the register, the content of memory location can be added to the content of accumulator. You can see in addm, content of memory location is added to the accumulator. In case of add B, you are observing the content of B register is added with A. So after that the result is stored in the accumulator register. So no two other 8-bit registers can be added directly except accumulator. So the contents of B register cannot be added directly to the content of C register. Okay, so naturally this is not possible. Add B comma C, this is not possible in 8085 microprocessor. Next is subtraction. In case of the subtraction, any 8-bit number or the contents of a register or the contents of memory location can be subtracted from the content of accumulator. So we can conclude that it is basically a one address instruction. Why one address? Because instructions are say sub B, say sub M. So here we are observing in case of sub B, we are subtracting the content of accumulator register with B register, and in case of sub M, what we are doing, we are subtracting the value of accumulator and M memory location, and result is stored in A. So in case of the sub B, the contents of memory location, content of register B is subtracted with accumulator. In case of sub M, the contents of memory location M can be subtracted from the contents of accumulator, or it may possible an 8-bit data can be subtracted. So SUI 05H. So what happens in that case, the content of accumulator is subtracted from the data which is given directly, and the result is stored in the accumulator register. So subtraction is performed in 2's complement form. Very simple. What is 2's complement form? So A minus 05. So I should write it down in this way. The 2's complement of 05, that is 05 A, the contents of B register. So I should write it down B bar plus 1. So B bar plus 1 is basically the 2's complement, and the result is going to be stored in A register. If the result is negative, Result can be a two possible options are there. Result can be either positive, result can be negative. It is stored in 2's complement form. So if the result is negative, it is stored in 2's complement form. For example, if the result is suppose 0 to, then 0 to h, then basically the result is minus 0 to h, then it can be you stored in this way. We should take the binary value of 0, and we should convert 2 into 4 digit binary number, then take the 1's complement and add 1 with it. After adding 1 with it, 1 plus 1 is 0, 1 1 1 1 1 1 1. So this is f, and this is nothing but your e. So fe will be your result. So the fe represents minus 0 2. So that is how the result is represented. No two other 8-bit register can be subtracted directly. It indicates that sub b comma c, that means b register value and c register value are subtracted. This is not allowed in 8085. Now next we have increment or decrement. In case of the increment decrement, we are observing the 8-bit contents of a register or a memory location can be incremented or decremented by 1. For example, if we talk about register, then we can observe that INR A, in that case the value of the accumulator register is incremented by 1, and the result is stored in the accumulator register. Next is we are observing that INR M, in that case the value of the memory location M is incremented by 1, and the result is stored in M location. So here we are using register incrementing register content, and here we are incrementing the content of memory location M. Next is same is applied for decremented. For decrementation, the instruction is DCR. So DCR A, it represents that the value of the accumulator will be the value of the accumulator minus 1, and similarly DCR M, which represents that the value of the memory location M will be the value of the memory location M minus 1. So this is basically deals with the accumulator, this deals with the memory. So this, in this case, the register content is decremented by 1. In this case, the memory contents is decremented by 1. Not only the content is going to be decremented, but also the address can be decremented. So 16-bit contents of a register pair can be incremented or decremented by 1. We all know that whenever we need to store an address into a register, a single register cannot able to hold that content for prolonged period of time. So what we do, we should use register pair, and we are using here register pair such as HL register pair. So if you suppose in HL register pair the value is say 9050, suppose we want to increment this address, then we should write INXH, then the address of 9050 is incremented by 1. Similarly, if we want to decrement it, we should write DCXH, then the value of 9050 will be decremented by 1. Okay. So next is increment and decrement can be performed on any register or any memory location. Okay, you can observe that we are performing increment on register, we are performing an increment on memory. Similarly, we are performing the increment on decrement on register, we are performing decrement on a memory. Memory is identified by M. Before writing INRM or DCRM, we need to specify what is the address pointed by M. So we need to write H LXI H, then the address, say the address is 9050. That means it indicates that HL register pair is pointing 9050. That means 9050 is the memory location. Then we can write DCRM or INRM, not before that. So this is a dependent instruction, DCRM or INRM. Okay, so let us take some questions from your side. Let us take some question from your side. Do you have any kind of questions? Do you have any kind of question, any kind of doubt till now? Moinak Roy is replying, no sir, there is no question, all is clear. I am waiting for other students to reply so that we can proceed further. Okay, Shubham is replying, sir, proceed, clear sir. So we can proceed further by explaining by explaining by starting with the add instruction. So let us explain the add instruction. So in case of the add instruction, it is the first arithmetic instruction that we have. We are observing that in add instruction, add is basically the mnemonics or opcode position. In the operand position, we can write either register or the memory location. Register is represented by R, memory location is represented by M. So our instruction is, suppose add R, you can write any kind of R here, either accumulator or B register or C register or D register or E register or H or L, any kind of register we can use. So in case of add A, the value of the accumulator is added with the content of the accumulator, result is stored in A. In case of add B, the value of the B register is added with the content of A register and result is stored in A register. Result means sum, because in case of the addition there are two things generated, sum and carry. If there exists any carry during the addition, that carry will be reflected in the carry flag. How? For example, say this is our flag register. We know the bits of flag register 1, 2, 3, 4, 5, 6, 7. 0 bit represents the carry flag. Suppose initially the carry flag is 0 and now there exists a carry after add operation. So this carry flag will be overwritten by 1. Okay, so this is what is happening here. So in case of the add operation, also the contents of the register and the memory can be added. So to add the memory, we should use addm instruction. Addm is a dependent instruction. We need to write LXIH comma any address, say 9050 address, we need to write it down. Then what happens, this instruction will initialize the address 90 at H, 50 at L, then 9050 memory address location is pointed by HL register pair. Let us assume there exists a value 07H. Now what happened, this 07H and the value of the accumulator, let us assume the value of the accumulator is 02H, these two will be added, and the result is 09H, and this 09H result will be stored in accumulator register. What is the carry here? Carry is 0, then naturally the carry flag will be set with 0. Okay, so this is happening during the addition operation. So after the addition operation, the sum of the addition is stored in the accumulator register. If the operand is in memory location, for example in this case our operand 07 is our operand, it is stored in a memory location 9050, then 9050, this address is specified by, should be specified by HL register pair or something that like that. Okay, so next, all flags are modified and reflected after the addition, such as after the addition the sum may be 0, then Z flag may be modified. After the addition the result may be negative, so sign flag may be modified. After the addition there may be a carry bit generated from third bit to fourth bit, so auxiliary carry can be modified. After the addition the parity flag may be changed due to the even number of ones or odd number of ones present in the sum. Okay, next is example add b, add m. These are examples of these types of instruction. After add, the next is ADC R and ADC M. ADC, AD stands for add, C for carry. So we are adding the register or memory to the accumulator with the value of the carry flag. So previous value of the carry flag should be into consideration. We need to add the content of the accumulator register. We need to add the content of the register that we are using, suppose B register using. Then we need to add the carry flag, and the result will be stored in a register. If we are using memory, we need to add the value of the accumulator, add the value of the memory location M, then add the value of the carry flag. Result will be stored in accumulator register. Okay, so result, here result means we are concentrating on sum, basically sum of the result. We know after addition two things is generated, one is summation and second one is carry. Okay, in case of the ADC we are observing that either register is possible or memory is possible, such as ADCB, ADCM. How many at operand fields or operand locations field are present? Only one operand field or operand location field is present, so that is why it is in one address instruction. That is why it is in one address instruction. Okay, in case of ADC we are observing we required only the opcode to inform that we want to perform ADC of instruction. To represent opcode we required 1 byte, so ADC is a 1 byte instruction. Okay, ADCM is an dependent instruction because to execute ADCM, first of all we need to initialize the value of the HL register pair by an address, say 9000 is the address. Then only we can write ADC instruction, say ADCM. Then only M basically denotes the value stored at 9000, otherwise not. Next is ACI, AC for addition basically, and I for immediate, and then we specified the 8-bit data. What we are doing here, we are doing an 8-bit addition between the value of the accumulator and the 8-bit data that supplied directly. For example, say ACI 07H, say value of the accumulator is 02, so value of the accumulator and value 07 is added. The value of the accumulator is suppose 02, so 02 plus 07, that gives us 09, which will be stored in accumulator register. If there is an carry, then it will be reflected by carry flag. So the value of the carry flag here in this case is 0 because no carry has generated yet. So the 8-bit data and the carry flag are added to the content of the accumulator. So sorry for the mistake, the carry flag is also going to be added here, as because 07 data we are supplying directly or immediately or explicitly inside the definition of the instruction. Hence we can able to understand that this instruction is in immediate addressing mode. In immediate addressing mode, it belongs to immediate addressing mode. How many byte it will take for representing it? It will take 2 bytes. Why 2 byte? 1 byte is required to express the instruction opcode, that is ACI data. So to represent the opcode we required 1 byte, and to represent the data 07 here, for example 07 here, 07 is a 2-digit hexadecimal data. In binary it is 8-bit. 8-bit means 1 byte. So we to represent data we required another byte. It belongs to one address instruction, because how many address or operand location or data locations is there? In this case only one locations is there. That is why it is in one address instruction. All the flags are affected or modified or reflected by the result of this addition. The result or the sum will be stored in the accumulator, and in this expression we are adding an 8-bit data and the carry flag that are added to the content of the accumulator. Please try to understand that not only the accumulator value, not only the value of accumulator and the data that is supplied immediately, but also the value of the carry flag is going to be added. Next type of addition related instruction is DAD. In case of the DAD instruction, we are observing that we can able to use any register pair when there exists an addition required between two register pair. We should use DAD. For example, addition of two 16-bit numbers, say, then we can use the DAD instruction. For example, the value of the HL register pair is suppose say 0101, and the value of the D register is suppose 0202. So what we are doing basically here, we are adding the content of L and E first, that is the LSB or least significant registers bits. After adding the content is 03, there exists a carry say 00. With the carry, the value of H, value of D is going to be added. Result is 03. This 03 is stored in H, this 03 will stored in L. So that is the main functionality of this operation. So after this operation or the 16-bit addition operation, result or sum is going to be stored in HL register pair. If the result is larger than 16-bit, then obviously the carry flag will set to 1, otherwise the carry flag will remain 0. No other flags are changed in this operation, because this summation we are storing it inside the HL register pair, not in accumulator. So that's why in earlier cases we are storing the result in accumulator. That's why if the value of the accumulator change, naturally sign flag, zero flag, parity flag, auxiliary carry will change. But here in this case we are storing the result in HL register pair, which is not accumulator. That's why sign flag, parity flag, zero flag, auxiliary carry, they are not affected. Only the carry flag will be affected. because there is a chance of an outside carry which can be either 0 or 1. If no carry is generated, then carry flag is 0, otherwise carry flag is 1. Example, dat B. So if I write dat B, then very simple, the value of the HL register pair, which is a 16-bit data, and the value of the BC register pair is going to be added, and result is stored in the HL register pair. Carry flag will be affected after this operation. Next is subtraction related instruction. Before explaining subtraction related instructions, I would like to take some questions from your side. Any question from addition related instruction? If there is no question, then please write it down in the YouTube live chat box. Sir, we do not have any question. If you have any doubt, then please do not hesitate. Write it down your question in the YouTube live chat box. If you do not have any doubt, then write it down. Sir, we do not have any doubt regarding arithmetic, regarding addition related instructions. Moina Roy is saying, sir, no questions, sir, all is clear. I am waiting for other students to reply. Aditi is saying, sir, please tell the carry part again. Okay, okay, I shall repeat. Next student is writing, no doubt, sir. Okay. So as per the request, I am basically discussing the carry part once again. So in case of the DAD instruction, what happens is that, let me select the pen. In case of the DAD instruction, what happens is that, first of all, value of L register, value of E register is added. Naturally, sum will be stored in L register, but there exists a carry, and that carry will be used while adding the H and D value. So whenever we are adding H register value and D register value, we are also adding the value of the carry flag, because during the addition of H, L and E, there may be a carry. If the carry is 0, then we should write 0 here. If the carry is 1, then we should write 1 here. So that is why the carry flag is used here, and ultimately the result of this is going to stored in H register. Okay. So in case of DAD instruction, only the carry flag is affected, because after the 16-bit addition, result may be of 17 bit. The the MSB bit, which is the 17 bit, is basically considered to be the carry. Okay, so that is why we are using this instruction. We are using the carry, only carry flag will be affected by this instruction. But in case of the accumulator related instruction, for example, say add instruction, what happens is that that all the data are stored in accumulator. For example, 7 6 5 4 3 2 1 0. So all the data are stored in accumulator, and the value of the accumulator directly affect the flag register. So if the sum is 0 0 0 0 0 0 0 0, then Z flag value of the sum is 0, then Z flag is obviously going to be 1. Okay. Next, if the value of the sum or the most significant bit of the accumulator is 1, that means it indicates that the result is negative. So sign flag is definitely going to be 1. If there are even number of ones, then definitely the parity flag is going to set with 1. If there exists a borrow from third bit to fourth bit during the addition, okay, so auxiliary carry flag definitely is set to 1. If there exists a carry after the 7 bit, so after the 7 bit there exists a carry, suppose, then what happens, carry flag must be set with 1. If the 8th bit value is 0, then carry flag will definitely be 0. So that is why the value of the accumulator, as it directly reflects the flag register, hence sign flag, 0 flag, auxiliary carry flag, parity flag and carry flag will be affected. But in case of the DAD instruction, the value is stored in HL register pair. HL register pair do not have any direct effect on flag register. That is why only the carry flag will change, other flag will remain same. Next is sub instruction. In case of the sub instruction, we are observing, first of all, sub is written in the opcode section and either R or either M is written in the operand section. That means we can use either sub B or sub M, this type of instruction. In case of sub B, what happens? The value of the accumulator and B in register are subtracted and result or difference of the subtraction is stored in A. The subtraction should be in the form of 2's complement, so B bar plus 1. Next is, whenever we perform sub M, then what happens? The value of the accumulator, value of the M register, M memory locations complement plus 1 will be done and the result is stored in the accumulator register. So in this way it is operating. So the contents of the register or the contents of the memory location are subtracted from the content of accumulator. In the first example we are observing that the content of B register is basically subtracted from A, and in the second example we are observing the content of memory location M is subtracted from the accumulator and difference is stored in accumulator. The difference is stored in accumulator. If the operand is in memory location, then its address is specified by HL register pair. Example, sub M. In case of sub M, we need to point it out what is basically capital M. So to point it out capital M, we need to write LXI H, then value of M, say value of M is 9000 H, that is the value of M. Then what happens? In HL will be filled up by 9000. The value of H becomes 90, L becomes 00. So it will point to the memory location 9000. Let's say there exists a value 01H, and let's say the value of the accumulator is 02H. Then what happens? We perform the subtraction between them. Okay, we perform the subtraction between them, and what is the result? Result is 01H, and that will be stored in the accumulator. Okay, all the flags are modified to reflect the result of the subtraction. Why? Because our summation, our difference is stored in the accumulator register. That's why all the flags are affected or modified. All the flags are affected or modified. It address of affected and modified. If it is stored, if the result is stored in a register pair, say HL, BC or D, then it may not affect all the flags. It may affect only the carry flag, because during subtraction we know there exists a borrow or there may not be a borrow. Examples sub P sub M, these are examples. Next is SDB. SB stands for subtraction and B for borrow. So subtract either the register value from the accumulator with borrow, or subtract the value of the memory location from the accumulator with borrow. So we are going to consider the borrow here. So the content of the register or memory location and the borrow flag, that is carry flag, are subtracted from the contents of the accumulator. Simple equation is the value of the accumulator or difference will be A minus B minus carry flag. If our instruction is SBB R or SBBB, okay. Similarly, the equation or micro operation of SBBM will be A minus M minus carry flag or borrow flag. So it is for the instruction SBBM. That means the value of the memory location and the carry flag are subtracted from the contents of the accumulator. The result of difference is stored in the accumulator, and the borrow, if it is generated, then it will reflect or modify the carry flag. Carry flag is also known as borrow flag. So if two registers are subtracted, A and B, there exists a difference and there exists a borrow, and the borrow will be reflected by carry flag. We need to understand it very carefully. If the operand is in memory location, its address is specified by HL pair. All the flags are modified to reflect the result of subtraction. So if we are writing say SBBM, then it is a dependent instruction, we all know. M is basically the memory location. M is basically the memory location. But what is the value of the memory location? To represent that, we require LXIH instruction. Say LXIH 9000H. That means the value of the HL register pair is 9000. Now we go to 9000 location, and the data value stored there is suppose 01. Now what happens is that, okay, we are subtracting the value of the accumulator. Say value of the accumulator is 02 and the value of the M 9000 location is 01H and the borrow flag is suppose 0. Then we are performing the operation and stored the result in accumulator, and the accumulator value will be 01H. This is nothing but your difference. And what is the carry or what is the borrow? Borrow is 00. This is nothing but your carry flag will be reset. That means carry flag will be 0. So we have explained two examples here. One is SBB and SBBM. Next is SUI. So SUI SUI 8-bit data. Naturally, as because we are observing there exists an I over there, we need to understand that it is in immediate addressing mode. How many bytes are required to represent SUI data? We require 1 byte for representing the opcode, and to represent SUI and to represent the data we require another 1 byte. Okay, so naturally if we are writing SUI say 01H, then 01H is our data. So we need to first of all write the opcode of SUI data, and then we need to specify what is the data. So subtract immediate from accumulator without any considering the borrow. So what is the equation? SUI 01, what will be the equation? The value of the accumulator and the value that is supplied directly, they are subtracted, and the result or difference will be stored in the accumulator register. The difference is going to be stored in the accumulator register, as because the all the bits of accumulator may be reflected or modified. Hence, as because accumulator has a direct effect on the flag register, so all the flags can be modified or reflected by the result of subtraction. I have already explained an example of SUI 01 data. What is happening here? But in case of the SBI, we are not only subtracting the data directly or implicitly given, explicitly given in the definition of the instruction, but also we are subtracting the borrow as well. For example, say SBI 01H. What is the micro operation written for that? It means the value of the accumulator, value data that is given here 01, and the carry flag will be subtracted, and the result or difference of this subtraction will be stored in the accumulator register. So 8-bit data and the borrow flag is subtracted from the contents of accumulator register. The result is stored in accumulator. Result means we know that after the subtraction there are two results. One is difference and another one is borrow. If my borrow is initially 0, value of accumulator is 02, then my difference will be 01 and my borrow will be 0. Okay. So all the flags are modified to reflect the result of subtraction, as because my difference is stored in the accumulator, and as accumulator directly affect the flag register, hence all the flags are modified and reflected to reflect the result of subtraction. Okay. In case of SBI, if you look at that, SB stands for subtraction, I for immediate. That means subtract immediate from the accumulator with borrow. So what is the data here? Here we are supplying the data, 8-bit data here. Okay, for the subtraction. So SBI 8-bit data we are using it here. How many bytes it will require? It will require 2 bytes, one for the opcode. First byte is required for the opcode. Opcode for what? Opcode for SBI data instruction. And second is we required another byte to represent the data which is explicitly specified. What is the data in case of the SBI 01H? The data is 01H. So that data we can able to consider as another byte. It is a 0 address, 1 address, 2 address or 3 address. Which address instruction it is? The length of this instruction is 1. That means it is a 1 address instruction. Why? Because we are observing that in the operand field, there exists only one Sorry for the interruption. Suddenly the PowerPoint has stopped, and we do not have any power backup system in this computer because there is a huge power cut off in my locality. So that's why I think I can able to complete this class within stipulated time period. Okay. Last 10 minutes of the class should be assigned for the examination purpose, as you all know. So we are talking about SBI. So in case of the SBI, there is an 8-bit data, so it is in immediate addressing mode as I is there. SB stands for subtract immediate from accumulator with borrow. Here in the operand field we can able to specify only one data, that is either 07 or something like that. So we require 1 byte for the data and we require 1 byte for the opcode. So it requires 2 bytes. It is a 1 address instruction because in the operand field we can specify only one data byte. That is why it is an 1 address instruction, because in the operand field or operand location field or address field we can specify only one data, not more than that. After this we can explain INR instruction, INR R and INR M. IN stands for increment, R for register. So INR R, and this instruction increments the register or memory by 1. So the content of register or memory location are incremented by 1 in this case. Example, say INR B, then what happens? The value of the value of the B register will incremented by 1 and the result will be stored in B. So any register can be used in INR, but in subtraction one of the register should be A. In addition, one of the register should be A. So in case of the INRB, we are observing it is basically an 1 address instruction, because either we can specify register or we can specify memory. It is in either memory addressing mode or register addressing mode. INR M, what happens? Your one of the source operand is stored in M memory location, so it is in memory addressing mode. In INR R, your operand is basically stored, or source data is stored in a register, so it is in register addressing mode. So INR B is in register addressing mode and INR M is in memory addressing mode. INR M is a dependent instruction. Before executing INR M, we need to specify what is the value of M. Say value of M is 9090H. Then what happens? The HL register value will be 9090. Then what happens? HL register pair will point the location 9090. The data value stored over there is suppose 03. Now what happens after INR M? 03H is stored. So M value is 03 plus 01H. So result is 04H. So the value of 9090 will be incremented and it will become 04H. So after the operation, the sum of the result is stored in the same place. That means either in B register it can be stored, or in HL register pair, or in the memory location it can be stored. If the operand is a memory location, for example INR M, what is the operand? Operand is a memory location. Okay, then its address is specified by the contents of HL. Look at that, LXI H9090. So HL register pair is addressing 9090 location. So we are pointing 9090 location. What is the data? 03H. So 03H will be incremented by 1. Examples we have already explained. Next, INXH. In case of INX, so X stands for indirect. So we are indirectly incrementing the value of a memory location or any place. In case of INXH, INX is basically your INX register is basically your opcode. What is the operand? How many operand fields are there? Only one. So it is one address instruction. As because X is there, we can able to understand it is in indirect addressing mode. Okay. So we can increment the register pair by 1. For example, say INXH, then what happens? Suppose initially the value of the H and L are 90,000, sorry 9,000. So after the incrementation, H remains the same, but L will be incremented by 1. So previously it is 9,000, now it become 9,001. So we have incremented successfully the value of HL register pair. Similarly, INX B, if we write, that means we are about to increment the value of the BC register pair. That is, suppose it is 9,000, after INX B it will become 9,001. Similarly, we can write INX D, that means we are pointing the D register pair. If the value of the D register pair is 8050, after incrementing the value becomes 8051. This is D, this is E. Okay, so the result is stored in the same place. So previously, before accessing the value, the result is stored in the D register pair. Before the operation, the source data is stored in D register pair. After the operation, the destination data will transmit into D register pair as well. So same is applied for BC and HL register pair. INXH, as because X is there, it is in indirect addressing mode. Okay, we are in decrementing or incrementing. We are incrementing the value of a register pair. Please try to understand. We are not decrementing the value of a register. Rather, we are incrementing the value of a register pair by 1. Okay. After INX, the next instruction is DCR. So DC stands for decrement and R for register. So DCR R and DCR M are two versions. DCR R, then suppose DCR B, then what happens? The value of the B register will be decremented by 1. Result is stored in the same location. Similarly, DCR M, here we are using a memory location. Then what happens? The memory location value will be decremented by 1. Result is stored in the same location. DCR M is in memory addressing mode and DCR B is in register addressing mode, as B is a register. But DCR M is a dependent instruction. So before executing DCR M, we have to initialize what is the value of M. Suppose the value of M is 9,000. So the HL register pair will initialize by 9,000. H value is 90, L value is 00. Then what happens? We point to 9,000 location and retrieve the value. Say the value is 03H. Then whenever we execute DCR M, the value of M is here 03H and we decrement it by 1. So result is 02H. 02H will be stored in M, that is 9,000. So this value will be overwritten by 02. So as I said, if the operand is memory location, its address is specified by the contents of HL register pair. The difference is basically stored, or result is basically stored in the same place. For example, in case of DCRB, it is stored in B. In case of DCRM, it is stored in M. Next is the content of a register or memory locations. The contents of register or memory locations are decremented by 1 here, as we are observing here. DCR-R or DCR-M, all of them are one address instruction. And we can able to observe how many bytes is required to express this. They require only 1 byte. So DCRB has a separate opcode. DCRC has a separate opcode. So we require only 1 byte to represent this instruction to the computer system, to the microprocessor system. Similarly, DCRM has a separate opcode than DCRB. So we require only 1 byte. So these are 1 byte instruction. They are one address instruction, and they are in register addressing mode or memory addressing mode. For example, DCRB is in register addressing mode and DCRM is in memory addressing mode. Our last instruction is DCXR. In DCX, so DC for decrement, X for indirect, and R is basically operand. How many operands are there? Only one. So needless to say, it is one address instruction. Next is, as because there is an X is there, so what happens? We can say that it is in indirect addressing mode. Okay, so what we are doing, we are basically decrementing a register pair. For example, DCXH, suppose the value of the HL register pair is 9051. So after decrementing, the value becomes 9050. Okay, so the micro equation or micro operation can be written for that is the value of the HL register pair will be HL register pair minus the minus 01H. That is the minus 01H. That is the equation for DCXH. Okay, just like DCXH, several other register pair can be possible, such as DCXB. In that case, we are pointing this BC register pair, such as DCXD. In that case, we are pointing DE register pair. Okay, so result is stored in the same place. The contents of the register pair is decremented by 1 in this case. So 9051, if it is the data, it is decremented by 1 and it becomes 9050. So that is basically the DCX8. How many bytes are required for DCXB or DCXAD or DCXH? There is only 1 byte required, because we need to store only the opcode of DCXR or DCXR value we need to store